It is not immediately obvious where the reverse speed dissipation zone fits. So let's slowly unpack that part of the four-pump zone story. In a typical centrifugal pump, the reverse speed dissipation zone starts at about 2.8 to 2.9 times the rated flow. In a mixed flow pump, note the different characteristics in all four zones due to the different design of a mixed flow pump's impeller. In a mixed flow pump, the reverse speed dissipation zone starts at about 1.9 times rated flow. In an axial flow pump, the reverse speed dissipation zone starts at about 1.6 times the rated flow. Where does the dividing line between the normal zone and the reverse speed dissipation zone come from? The answer to that question comes from looking at graphs of flow versus torque for each pump type, using similar dimensionless terms. For a centrifugal pump, the torque curve in the normal zone drops below the zero torque value when the flow is about 2.8 or 2.9 times the rated flow. Below this point, the pump's torque characteristic is negative. This means that at a forward flow higher than this point, a pump is no longer able to turn in the forward direction. And looking at the torque curve for a mixed flow pump, here is the point at which its curve drops below the zero torque value. The dividing line is about 1.9 times rated flow. And here is the same thing for an axial flow pump. The dividing line is about 1.6 times rated flow. Answer: a pump's torque characteristics define the start of the reverse speed dissipation zone. Allowing the pipe system to drive excessive forward flow through a pump and letting the pump move from the normal zone into the reverse speed dissipation zone should be avoided. Damage can occur from the shock load on the mechanical drivetrain. This may not be an issue if the motor is not running and the pump set is just freewheeling, and the rate of change in forward flow rate is slow. So let us return to looking at the steady state characteristics of a pump, operating in the normal zone, fitted with a non-return valve on the delivery side of the pump, and performing the function of a lift station, lifting water from a lower elevation to a higher elevation. Can this arrangement end up operating in the reverse speed dissipation zone? The answer is likely to be no in typical installations. For a lift station, the pump has primary control of how much flow is able to be delivered through the system. Even during transient surges, the water momentum is not likely to grossly increase the forward flow rate through the pump. In a lift station, everything other than the pump and the water's forward momentum is working against flow in the forward direction. Perhaps a lift station with a large diameter, very long suction main and a short delivery main could be driven into the reverse speed dissipation zone by transient surges. This situation would have a lot more water momentum on the suction side of the pump than on the delivery side. Let us swap to another scenario and consider a pump used as a flow booster, that is, increasing the flow rate through a gravity pipeline. A non-return valve on the pump delivery removes the need to consider either of the reverse flow zones. In this situation, gravity is able to transfer flow in the forward direction when the pump is off. Or consider a scenario using a flow booster to directly supply customer demand without any terminal storage on the delivery side of the pump. In flow booster scenarios, gravity and customer demand have the ability to dictate the forward flow rate through the pump, and extreme transient surges have the potential to accentuate forward flow for a short period of time. One extreme transient event may be a rapid major pipeline rupture. Consequently, in a flow booster scenario, designers should give due consideration to both the normal zone and reverse speed dissipation zone. As well as understanding where the pump will operate while the motor is running, Consider how much forward flow through the system may generate in an extreme scenario, e.g. a pipe burst. Could any system transients take the pump into the reverse speed dissipation zone? In this situation, best practice is to install a large diameter gravity bypass, complete with its own non-return valve, around the pump set to remove this risk. Large forward flows grow through the bypass. Only minor forward flow goes through the pump when the pump is off. It is these best practices involving a non-return valve on the pump delivery, and where necessary on booster pumping stations, a bypass pipe around the pump, that allow civil engineers and hydraulic engineers to sleep comfortably at night, believing that pumps operate safely if they can physically only operate in one zone.